The first one is going to be a duo presentation by Laura Knott and John Pope. They're both from Old Town Glass from the US, over from the US. So a warm welcome to the owner, John Pope, and Laura Knott. Laura is a project engineer specialized in high-end residential glazing projects, as I think the core business, one of the core businesses of Old Town Glass. And I found it interesting. She has just received a passive house certification. So give a round of applause already for their presentation.
Thank you for coming to our presentation. Again, I'm Lauren.
I'm John.
We should have called it Bending Boundaries, but we're going to be presenting today what we believe to be was the first S-curve cold bent insulated glass. Back in 2017, our client approached us with a dream project, an unobstructed panoramic view of the Pacific Ocean, which you can see here. This is a picture of the job site before we had started building. Here you can see the plans of the second floor of this home, where there's over 50 meters of continuous cold bent glass, which is all highlighted in blue. And then in the orange zone there, you can see an inflection area. And the client specifically requested not to have a mullion at this zone. So we had to figure out if we could create an S-curve shaped glass. So 6 years later, and lots of calculations, lots of collaboration with many different engineers and experts from different countries and different backgrounds, we were able to figure out how to make this happen. But before I get into the specifics of the project, I just want to clarify what type of bending I'm talking about. Hot bending may be the most familiar type of bending process, where you heat the glass to 600 or 700 degrees Celsius until it softens into its new curved shape. And then you quench it so it holds that shape. But today I'll be talking about a cold bending process. And there's kind of two different types of cold bending. The first one being on-site, where you take a flat piece of glass and you push it into a curved frame, and that curved frame is holding it in its curved shape. The other type of cold bending referred to in industry is also known as lamination bending, and for this presentation, I'll be referring to that as cold lamination bending for clarification. The benefit of cold bending is mostly that you can attain a much higher clarity due to not having to heat up the glass like you do with hot bending. However, there are more limitations to the curvature you can attain, and you also have to conduct more rigorous prefabrication calculations to kind of figure out how much stress the glass can really handle. So cold lamination bending is essentially maybe an extra step in the lamination process, where the sandwich entering the autoclave is also in a curved shape. So when it exits the autoclave, now the shear stress in the interlayer, which is bonded to the glass, is holding that curved shape. However, the glass is still going to remember that it was flat, so it has a tendency to rebound. And you can see that demonstrated here in the large graph, and zoomed out is the smaller graph in the upper corner. This black rectangle is the bigger graph. So for example, the green arc is a typical single radius curvature that someone might want to achieve with a normal cold bent glass. And the red is what you might expect to actually receive after fabrication. So you end up with some more flatness on the edges and a somewhat more parabolic shape rather than circular. So due to this concept of rebound, you have to kind of anticipate how much rebound you might experience, which is related to the glass thickness and the number of interlayers, and include that in your calculations before you can start fabricating. So we worked with Sedak to figure out if this was going to be possible. So back to the plan view of the project. This is a zoomed in picture of the S-curve area. So it transitions from the concave area of the great room, which in this project was kind of the center of the home or the living space, into the east hallway. And again, we couldn't have a mullion here because the view was spectacular. zooming back out, you can see the geometry in this building is quite interesting and quite unique. You can try to count how many circles are here. And again, the East Hall and the Great Room, S-curve right in the middle. So the initial design was supposed to be 2 radii with a single inflection point at the middle. And the buildup of this glass was an insulated unit with laminated lights on both sides, 6 millimeter laminated. It was 3.2 meters tall, almost 5.4 meters wide, with about a 7 meter radius on each arc. However, when Sedak began their feasibility analysis, what they found was that the transition area between one arc to the next was going to have an extremely high stress area. As you can see in figures 2 and 3 here, representing the stress in the glass, there's a very sharp change in color. So this was not only going to be problematic for fabrication feasibility, but also this would be a very high distortion area, and also risk of glass failure. So they had to rethink the shape of the S-curve and think, what can we do to make this still possible? And what they did is they tweaked the curvature of the S-curve just slightly to sort of minimize the abrupt transition in stress. So I'll toggle back and forth, and if you look at figures 5 and 6, this is the initial shape, and this was the improved shape. So you can see that there's a smoother transition in the stress. And the way that this was achieved was essentially by transitioning from one curvature to the next, rather than having, so in this slide, I'm showing 2 curvature combs. The top one is the original shape, where each line is representing the radius at that specific point in the arc. And you can see there's one radius up here, and then it immediately flips to the other side to the second radius at just one inflection point. But the improved shape starts with one radius, and then it slowly decreases the curvature as it approaches the inflection point, and then slowly increases it and transitions to the second radius. So essentially, we end up with infinite radii rather than just 2. And rather than one inflection point, we have more of an inflection zone. So here's a drawing approximating the new S-curve shape to 0.3 millimeters. And you can see it divides the shape rather than in 2 sections into actually 13, one of which is actually flat. So another way to describe this new shape, which again was quite subtle, and it didn't affect our ability to keep the design intent as it was supposed to be. The curvature was similar to that of a clothoid, also known as Euler's spiral. And this is a type of curve where the curvature changes linearly with the arc length. And it's often used, many of you have probably heard of it before, it's often used when designing railway tracks and roads to prevent trains from flying off the tracks and cars from crashing. So this is some of the equations and the graph, but essentially it's an equation that helps you determine the smoothest transition from one curvature to the next, or maybe just a flat section to a curved section. So after all of that, we were able to determine that the S-curve would be feasible in theory, but the next question was, could we actually produce it within a tolerance that would be installable, and would it work in real life?
So one of the things we had to do is, once the engineering was determined and the decision was made, we know it will work, we had to actually put that into practice. And what was unique is during the pandemic, a lot of this was happening, so there wasn't the ability to travel back and forth to the various suppliers in Europe that we were working with. So Sedak made a 1 meter tall mock-up, which you can see. We actually shipped that to California. Skyframe, who we use for the track system, and we had to do modifications to that track system to actually take what was produced in the glass unit and combine it with our 1 meter tall mock-up. We had to bring, even though both companies are in Europe, we had to bring everything to California and put it together, which made it a super unique challenge. And as you can see, we basically had templates made along with life-size parts and pieces. And those templates showed where we had potential pinch points, which actually helped us as we moved from the glass portion of this into the frame portion. And what you can see here is we actually took what we learned from what was done in Petaluma, where our warehouse was in California. We took those learnings, and then when travel was allowed and our frame was ready, we took the same templates to Switzerland and laid our stainless steel glass template into the track. And Lauren can talk about where we ran into some pinch points, and then these learnings were then applied into the field for installation.
Yeah, so we were using an aluminum skyframe track, and so typically an S shape is not super normal for them either. So the skyframe track had 5 different sections that needed to be assembled, all with their own radii. And again, our glass had close to 13, so to make sure that the glass would fit in the track was a very big issue. So over on the photo on the left, you can see we dropped our laser cut steel footprint of the glass into the fully assembled track as kind of a mock installation. And what we found was there was no more than really 5 millimeters of deviation, which was enough for us to manage with some adjustments during the day of install. The last step of kind of quality control that we did was producing yet another mock-up piece of glass. This was a full height laminated panel that we had a point cloud scan conducted with the help of Sedak to basically verify that the curvature was matching up with what it theoretically was supposed to be. So on the left side, you can see a surface deviation represented by those colors. And in the upper left is where we saw the most deviation, but it was no more than 5.7 millimeters, which was, again, within our tolerances. And this glass is flexible a little bit, as well as the track has some adjustments. So we also took the point cloud scan and dropped it into our CAD model of our frame as another mock installation, because again, we're trying to get ahead of any potential issues that might come up the day of install. And what we found is that it would probably fit.
And fitting was good news because the project site, about 3 hours north of San Francisco, was super remote. We had unpredictable weather. Even in the summer, we have significant amount of fog, wind, rain, and poor cell phone reception. So one of the things on the installation and logistics side is this is the good section of the road getting to the job site, and this hairpin is the better hairpin. So we wanted to do as much dress rehearsal and choreography as we could, so that on the installation side, we have a very unique piece of one-off glass that we have to get installed. This isn't a typical, downtown setting where you can pull up a semi and offload it with a tower crane. In fact, the homeowners association where the project was built would not allow us to put up a tower crane or have permanent, so everything had to be brought in. This is preparing for the installation.
Removing the S-curve from the crate for the first time. And luckily we had good weather. You can see the fog just looming maybe half kilometer off the coast.
And so on installation day, we made a plan of a 2-day period. And during that 2-day period, the focus was on the S-curve and then the 2 additional 8-meter pieces that were next to it, which those in themselves were a whole nother set of challenges, because we had, for the S-curve, we had to have a custom adapter made for our suction cup unit, for a unique geometry. Most everything is, concave or convex. So putting that plan together, we were then able to pick the glass and install it into the skyframe track. And one of the client's requirements was they wanted their sliding door system and the fix units to not be separated. So initially, when we started this project, we said, okay, let's make a custom milled facade system. Let's do a custom track, and we could structurally glaze everything into the opening. The client wanted to have a very clean line when we moved around the building from a fixed to an operable unit. And to do that, we had to take a frame system that was designed for much smaller units and actually custom design with EOC and modify that unit in order to have a system that we could put this glass into, but it was not your typical facade system. So we actually had to take and lift these pieces of glass up and then drop them back down into the system. And so what you see here is we had a successful installation in 2023. You can see where the S shape is. And one of the things that's unique is, we're focused on that corner down in the bottom with our install, and through the use of all of the templates and kind of the choreography and the 3D models, we knew exactly where our tightest tolerances were on the day of installation, which allowed us to really make sure, one, the glass didn't get damaged going into the opening, but that we could fit it into place and have enough room for the screws between the S-shaped piece and the next curved unit. Because of seismic and a lot of the other things, we had zero room to spare. But in the end, it worked out.
So on July 26th in 2023, we successfully installed not only the S-curve glass, but the adjacent large cold bent panels, as you can see here. And one of the main takeaways from this presentation and this project is that it really takes a village to make something like this happen. This was a huge team effort. This was the day of installation. There was many people involved, some of which are actually here in the audience today. And we couldn't have done it without all of them saying yes to a seemingly crazy idea. And that's also why we're all here today
including the architects here today. And his vision kind of gave us all an opportunity in the industry to kind of come up with something unique for a private residence, which it's kind of fun when you look at something and say, you know what, you have a view. You don't want to disturb that view, so let's get rid of the mullion. And if that mullion needs to be an S-shaped piece of glass, that's the end result of something coming together.
So thank you all for coming to this presentation, and also GPD, so we can all continue to push the boundaries of the glass industry.